Hey everybody, this is our applied deep learning project. My name is Michael,
My name's Sam.
Vincent.
and we're going to start off with a brief overview and then go into specific topics.
So we will go over the code later. This is just a structure of our submission for your reference.
Yeah, so we ended up training our own CNN that ended up working the best, that had about an 87.6% test accuracy, and using our evaluation metric, an 85% area under the curve for the ROC.
So I'll talk a little bit about the pre-processing. So for the pre-processing, what we did is we looked at the images of the slides we had, and we only passed in ones that we thought had proper data. So we would download it, put it into a bucket, and then when we explored the code, we would just load it from the bucket. So a little bit about how we pre-process data. What we would do is we would slide across the image. If there was more than 80% gray pixels in any given patch, then we would move on to the next patch and disregard it. Or else we would collect the zoom level 3 and 4 images and also the Y label of the patch. As you can see below, the parameters we use are 299 by 299 window size, zoom level 3 and 4, and we'd also stride 100 pixels, so that's how much we stride or every time we slide across the image. And the Y label needs a little bit of explaining. So basically, for the Y label, we looked at the upper left-hand corner of zoom level 4. And there's a very specific reasons that we chose this. If you look at the zoom level 4 and zoom level 3 of the same coordinate pair, so this is one coordinate pair just of zoom level 4 and zoom level 3, we see that it's zooming in on the upper left-hand corner. And this is only because of how OpenSlide works. And because of that, on zoom level 4, in order to determine if it is cancerous or not, we look at a 128 by 128 upper left-hand window, and if any pixel in that is cancerous, then we label the whole image as cancerous. The reason we chose that, again, is because of how OpenSlide works in that it zooms in on the upper left-hand corner.
So I'm going to briefly go over our modeling approaches. So before we prepare our data set for training, and then we had a training set, but that was very imbalanced, and we thought that this could bias our result. And so we adopted the downsampling approach, where we artificially constructed a separate training set to balance the data, where we randomly sampled non-cancer samples to match the number of cancer samples. And for validation, we randomly sample 800 data points from the testing slides. So we first used transfer learning just to establish a pipeline. So we used a reinception V3 network with pre-trained weights from ImageNet. So the way we did it is, for each data point, which has two zoom levels, two images, we extracted features independently for each of these two images using Inception V3, and then we concatenated the extracted features into a single vector. And then we only trained a top consisting of a single dense layer with 64 nodes. This ended up giving us only mediocre result. And then we moved on to building our own CNN architecture, which we named BroNet. So this network takes in two input images, again for each data point, two zoom levels. And then for the zoom level 3, we use 3 convolution layers and 2 for the level 4. The top has, again, 64 one dense layer with 64 nodes and one single dropout layer to reduce overfitting. So the training on the artificially balanced data set looks like this figure right here. We only train Inception for about 10 epochs because it has very few trainable parameters. So for the BroNet, we trained for about 30 epochs, and we saw overfitting at about 20, where the validation accuracy started going down, but the training accuracy was approaching 100%. So we retrained BroNet from scratch, but for 20 epochs, and we used that as our final model to produce heat maps. But we also reasoned that because the task itself is intrinsically imbalanced, meaning that this is not a task where the training data we have is limited and imbalanced, but the task is has a balanced outcome. Because this task itself, the test data will be imbalanced as well. So we also train a BroNet on the full training data without downsampling, just to compare how it will perform. We decided to let the data speak. This turned out to produce better heat map than BroNet trained on artificially balanced data. And so this is a model that we ended up using for all of our subsequent heat maps in this presentation.
Yep. So I'll be talking about the evaluation now. So basically how we evaluated it was we chose 3 test slides in the beginning to hold out. These were 84, 94, and 101. And how we generated the heat map was we just slid the 299 by 299 tile over the image again, and we had about 400 patches on zoom level 4, which was 7424 by 6000-ish resolution. And we just predicted the probability of each little tile on this zoom level 4 image. So here are some heat maps. So as you can see, this one caught the Cancer right here and the Cancer right here pretty well. We do have some false positives though. Over here, this one did not do as great, although we did catch all the Cancer that was labeled Cancer over here. As a matter of fact, however, there were many false positives, including all along here, and we'll talk about false positives and false negatives later, and why which one's more important. And this one actually did surprisingly very well. So right here, and the Cancer over here was all caught, as you can see from the ground truth on the left. Yep, so basically the first thing that we did for evaluation, and this isn't like our actual evaluation metric, was we just looked at all of these standard ML performance metrics that we show here. This is how our model did. We had around an 87.62% overall validation accuracy, confusion matrix looking like this, and then recall and F1 score. The evaluation metric that we actually chose was the area under the curve for the ROC curve. We decided this because of a couple reasons. The first reason was because the Chameleon 16 challenge was originally using a metric very similar to this. So we decided that this would probably be a good metric for our heat maps also. The second reason was that because this metric of the area under the curve of the ROC basically tells us how well our classifier is at distinguishing between 2 classes. And that's what we want, right? So an area under the curve of 50% is basically saying that our classifier is like blind guessing. Anything above that is pretty good, I guess. A little bit better. 100% is the best. The only drawback, as we'll see in the next couple slides, is that on slides with little Cancer, this can be a little misleading. So the first ROC curve that we get is a 68% on this image that has a couple Cancer regions right here and right here. We have a couple false positives, and so we see about 68%. On this one, surprisingly, we actually get 100% almost. And the reason why this one might have gotten this performance is because there are actually very few ground truth Cancer regions in our test data, the ground truth test data. And as you can see, we have a bunch of false positives here, but the majority of the pixels in the image and the majority of the slides or patches in the image are actually just not cancerous. And so because there were so many not cancerous that were classified correctly everywhere, basically, this basically drove up the ROC curve. And looking at the false positives, this only made like a minor dent on the ROC curve. And we argued that this actually kind of preferred because we would rather have a false positive than a false negative, because a false positive in this case is basically telling the pathologist to look closer at these areas, in which the pathologist could use their human expertise to just say, look, these aren't cancerous. It would also remind the pathologist to look at this area, which is cancerous, which would be a very good reminder. However, if we had false negatives, say this was a false negative, then we wouldn't have this area at all, and we would basically miss a cancerous region, which would be more harmful than a pathologist just checking again on the supposedly cancerous regions, saying that they're not cancerous. Because again, it's for assisting, not deciding. Finally, this is the ROC curve for our pretty well classified heat map, as 85%, which is around what we would expect. And there are a lot more Cancer regions, so we get, I guess, a more balanced ROC curve. And these were our final numbers.
So for future work, obviously we can use more training data. And then we could have a bigger architecture in order to handle that increased amount of data. We also want to try to use a custom loss function in order to penalize false positive more. But again, we need to keep in mind of how this will impact our false negatives. Finally, we can always further tweak the hyperparameters of the CNN. And if we have more time, we could produce a more fine-grained heat map. This is just a proof of concept work. Thank you very much.
Hi guys, so I'll be talking a little bit about the data collection notebook that we have. So this is the data collection notebook. We have basically what we're looking at is we're looking at these 7 slides. At the very beginning, we install the packages we need, and then we import them. And then we're going to define certain functions we need, for example, read slide, find tissue pixels, and apply mask. And then we're importing the data from the bucket here because these .tif files are very large onto Google Colab. And then here we're just basically exploring the data, and this is the slide image that we're exploring. This is its mask image, and then this is the mask image overlaid onto the slide image. And then here are the tissue regions using fine tissue pixels. And so here's where, that's all part of the starter code. Here's kind of where our code starts. This is the data extraction and collection. So here we specify window size. We specify as 299 by 299. Here we're just testing a function that we created called test grayscale. It basically gives you the amount of gray in a certain 299 by 299 window. Here we are basically exploring the how it zooms. What we notice is that at the level 3, it's zoomed in onto the level 4 image on the upper left-hand corner. So that's what we're testing here. So here's some basically pre-processing functions that I talked about: test grayscale and test mask image. So test mask image is how we're figuring out, test mask image is how we're figuring out whether to label the region 1 or 0. And we do that by basically checking, the upper left-hand corner, as we can see here. And here we have a function called create train. And basically what we do is we input an index, a window size, and a level, and a stride, and then it will basically create our training set for us. So here we iterate over 7 of the slides, 4 for training, and then 3 for validation, and then we save it into a pickle file, and then we export this pickle file out so we can use it for the next notebook.
I'm going to go over really quickly about the notebook that we used to actually perform the deep learning. Loaded the data, and then we constructed our data sets as mentioned in the presentation earlier. And then so here is the Inception 3 model. So it basically takes in a data matrices and then it convert them, extract the features using the Inception V3 model preloaded. And then it's simply a sequential with 64 nodes in a dense layer to do the classification. For a CNN model, because we need 2 different inputs, so we actually used the Keras functional API to take in 2 different inputs, implement an architecture that we designed. And you can see the training is pretty good. And then the rest is our evaluation.
So finally, we have the evaluation code. What we have here is the starter code functions. Over here, we take out the raw images, and we predict over the test images of there are 3, 84, 94, and 101. These are all functions for predicting over them. Prepare for predict basically goes through the image that we want to predict over, the one that we want to generate a heat map over, and we basically make a dictionary that has the coordinates of each place that we want to predict over, and the 299 by 299 patch that we want to predict over as the value. So we start predicting here. Basically, we run the code here to predict, and we choose the index over here. This index is basically all you need to change. So 94 is the one that we chose for this one. And all of this pretty much just goes through prediction. This is where we use our CNN to predict. Predicted scores, we zip into a dictionary where the coordinates are mapped as keys to the scores now. So the scores are somewhere between 0 and 1, and it's the output of the sigmoid function. Finally, we visualize our heat map. We do this by just going over each kind of 288 by 299 by 299 tile and basically assigning it the probability, or a heat map based on the probability that we had for our sigmoid function. That's all in the dictionaries that we created before. We have that over here. Then we look at our ground truth. Finally, we have our evaluation metric. The first is patch level evaluation that we talked about in the presentation. All of this is just general performance metrics for machine learning stuff, precision recall F1, and our confusion matrix. These are some example images that you can look at. And finally, we have the area under the curve for the ROC curve. We just use the built-in ROC curve function from scikit-learn to get this. First, we find the ground truth. So we need to match one-to-one how many 299 by 299 tiles there are in the predicted probabilities with this. So we get the same number. I believe there are about 480 of them. So 480 tiles to look at. And we just make sure that this is okay. This is just some checks. Make sure that this does have a tumor. This does not have a tumor. And finally, we get the ROC curve. And a confusion matrix we looked at to make sure that we indeed did have mostly true negatives and some false positives, but only one false negative. Thank you very much.
Thank you.
Thanks. All right, who's gonna upload this boy?
Woo!